I hope you find the presentation appropriate, because what I've tried to do for myself, I'm not a geneticist, by the way. I'm a metabolic physician. My usual work consisted of obesity, diabetes, bone biology, osteoporosis, Paget's disease, electrolyte disorders. Those are the kind of things, that's my bread and butter stuff, but this is icing on the cake. But just to get going on alkaptonuria, I mean, there's a very strong link between alkaptonuria and genetics. I don't know whether you guys are aware. Mendel's inheritance laws were completely forgotten about, and it was remembered when this man, Archibald Garrett, was working on this group of patients in Great Ormond Street. He recognized that the patients he was seeing, there's a familial nature to the disease. And of course, it was this other person, William Bateson, who was a scientist, who reminded Garrett that these patients were obeying Mendel's laws of inheritance. So this was really the very first link to inheritance and disease. Okay, they didn't know anything about genetics or genes or anything else at the moment. So it is quite, Garrett is still being talked about as a sort of God, if you will. So there is a genes connection between alkaptonuria and the whole genome sequencing. And of course, he created the field of inherited metabolic disease in 1902 by talking about it for the very first time. Thank you. So what is alkaptonuria? It's a monogenic disease. It is a very rare disease, what's called an ultra-rare disease. It's about 1 in 250,000 to 1 in a million. The carrier state is about 1 in 500 for the disease. And what the problem lies in the homogentic dioxygenase gene, which is deficient in AKU. And if you look at this pathway, I suppose I have to put here dietary protein, and we consume about anything from 80 to 100 grams of protein a day, of which there's about 5 to 10 grams of tyrosine a day. And that tyrosine, we only need probably 0.2 grams a day. So that means the 95% surplus tyrosine has to be degraded and not lost to the body, and it's done through this metabolic pathway by conversion to a glucogenic substrate and a lipid substrate. So that is what happens in health. In AKU, this enzyme is missing, homogentic dioxygenase, which means you can't metabolize homogenic acid, which then accumulates, produced in excess, accumulates in the body tissues, in the circulating bloodstream, and is also excreted in the urine. Okay, so I have the next slide. So this enzyme, as you can see, is quite complex. Okay, so there are 6 monomers, and the 6 monomers become first a trimer, and there are 2 trimers which then join to become an hexamer. I mean, this is such a complicated process that it was just amazing to me that we are struggling to find a relationship between the enzyme and the phenotype. We are not seeing the urine homogenic acid or the circulating homogenic acid tracking to mutations we are doing. Okay, and I have absolutely no idea why, but I'm guessing it might be the fact that the dietary protein is swamping everything. So what we really need is a different methodology to see if the different mutations have different capability to break down homogenic acid, and we haven't done that yet. So I have to go. And this is, as you can see, a 50K a molecule, and you can see the chemistry of that. Can I go forward? But the important thing also is the homogenic acid is the place where the aromatic ring is broken down and becomes a linear chain as well. So it's quite an important reaction in biology. A lot of the knowledge, as you can see, is quite old. I mean, which gives us a wonderful opportunity, blank slate, to do what we like. The heterozygotes don't get the disease. Okay, so you need to have either a homozygote or a compound heterozygote to get the condition. So you got it is an autosomal recessive disease. Okay, so in normal person we were told, based on this data, that we've got the capability to break down nearly 1.6 kilograms of tyrosine a day. I'm not sure I believe that, but that's what we've been told. Okay, based on studies done in 1974, and in the heterozygote you can still break down about 800 grams per day. Okay, I'm not sure I believe that. And this is the amazing thing about the plasma levels, or the levels of homogenic acid. So in a normal person, you're struggling to find a blip of homogenic acid. It's hardly anything, even with the most high sensitive tandem mass spectrometer which we have. We just barely pick it up, and 70% of normals we don't find it. Okay, in alkapnuria you can see it is about 1,000-fold higher in the blood, and in the urine it's a further 1,000-fold higher. So the urine, really, the kidneys are safety outlets, and if you get renal failure, of course your disease is much more accelerated. We're talking genes, so I suppose I should say that it's located on chromosome 3. And again, you can see as I go along, I'll present some data on the mutation that we have seen. Can you go? And you can see there are active sites, there is stability issues, there's a hexamer formation issues, and analysis of all the recent analysis of all the mutations that we have seen, you can see the interface, surface, core, active, and you can see all kinds of chemical characterization of the mutations. Despite all of that, we haven't really pinned down the genotype, the HED genotype to the homogenic acid, either in the blood or in the urine. Okay. So any ideas, if you've got any brilliant ideas, anything we haven't thought about, we would love to hear about it. Okay. My own feeling is I think it's the diet, probably. It's such a huge amount that we don't need it swamping whatever little variation there is. But I might be wrong. Okay. Can you go forward as well? As I said in the previous slide, I say it's all or none loss. So therefore what we're saying in the phenotype is all or none. So in AKU, you get either you have a lot of homogenic acid, and in normals you don't have, or in the heterozygote you don't have. It's as simple as that. And this is a classical autosomal recessive in one family, and we can track it back if we go forward. And this is actually quite old. It's a bit dated. This is 2016 data, and you can see it's a 14 exon gene, and we are also seeing intronic mutations, not just exonic mutations. As I said, I'm not a geneticist. I wish Andrea Zetkova, who is the keeper of the HED database, was here to talk about a bit more about the genetics of it. I'm not an expert on that, so I'm not going to spend too much time telling you about it. Can we move forward? To summarize that, most of them are single nucleotide polymorphism, which is really great. I mean, one of the things we're also considering is gene therapies and things like that. When you're thinking about that, it's good to see, like a lot of other conditions, most of them are SNPs, but you can see you get a whole host of other things as well. And we have also now seeing intronic complete deletions as well in the intronic area, where previously we had a situation where we found one mutation, but we were struggling to find another one because we were concentrating on the exons. So it's quite, and this is why I think the whole genome sequencing might be interesting in terms of clarifying this further. So for us, so we are interested in alkapnuria, so therefore we have to collect the genetic samples. So the way we have done it is through two approaches. Both of them began in 2011. In 2011, we were invited to apply to become a centre for alkapnuria in Liverpool, which we did, to highly specialised services, NHS England. And in 2012, April Fool's Day, 1st of April, they said, you'll have a centre. So we started, our first patients came in June, and a lot of patients, about 76 patients we've collected genetic material on through there, and we have probably the most extensive phenotyping of AKU anywhere in the world. Without a boast, I'm sure we are the International Center for AKU now, okay, not the NIH, National Institutes of Health, we are, okay. They look at us now and we get patients from NIH coming to Liverpool as well to be treated. The other one was also in 2011, so there was a European call for rare diseases, and we applied in 2011, stage 1, stage 2 process. We got a €6 million grant to carry out a series of clinical studies in alkapnuria, and that has finished in January this year, 6 years and a quarter, and we're waiting with bated breath to hear what the outcome is in terms of decision by the pharmaceutical company, whether they're going to go ahead with marketing authorization. So for us, the material has come from these two. So in the National Center, as I said, we had about 76 samples, and in the Develop a Cure project, we had 138 patients with alkapnuria for a 4-year clinical trial using a drug called nitisinone, which again I'll come to. So, and as you can see, there's a dose response study with 40 patients, and there's a cross-sectional study to decide when when the disease actually takes hold in a process called ochronosis, and I'll come back to that in a minute. There were 32 patients in that, it was actually 30, and 138 patients in the SONIA 2 4-year clinical trial. So, can you go forward? And of course, this is the National Alkap Center. As you can see, it's a one-stop annual service model, and we have a very large multidisciplinary team, people from all over the UK. Well, that's wrong. It's actually only people from England and Scotland who are eligible to come for free. So there's a postcode lottery. So people from Wales are not eligible to come for free, so they have to fork out. Same with Northern Ireland. And they get nitisinone freely given to them. No need to worry about fighting for it locally. And this has helped us to phenotype patients really extensively. So we have done a lot of investigations, so we know everything about them. Okay. I was just trying to get this information yesterday. So of the 138 in SONIA 2, 71 individuals were related. Okay. There were 26 families, and there were 71 of them, more than half were related. A lot of these were Europeans, because the UK patients were not eligible to come to the clinical trial, because they already had the National Centre where they could get NAC nitisinone for free. So ethically, we couldn't actually justify putting them in a no treatment arm. So all of these are European patients, and of course the NAC, you can see it's a little bit different, probably because intermarriage is much less common in the UK. There's still about 30% of them are Asian. And there's a lot of intermarriage in the Asian group that we have in the NAC, and again in the 8 families we've got about 18 individuals in there. Whether we can do anything special about them, I don't know. Some of the families are quite long, quite big. There are about 10 or 12 members in a Jordanian group. So again, it's just food for thought to see whether there's anything we can do with larger families in there. Okay. So this is as far as the standard genetics is concerned. One of the things I would love to understand is we did a postmortem on a patient who died in 2005. She was 74 years old. She had carcinoma of the ovary. She had left her body for medical research, and we managed to do a postmortem on her. When the postmortem was carried out, she had very patchy ochronosis. So ochronosis is where the homogenic acid binds to tissue and causes the pigmentation. I've got some examples of that. The question is, why is it so patchy? So the question is it because some healthy tissues resist binding, or is it damage to tissues that causes them to bind? So we don't know. And whether that, so if that is true, then HGA is just a marker for tissue damage. If so, is there anything we can do? Is there anything that will show up when we do whole genome sequencing? I don't know. So again, it's just sort of thinking about the process. Okay, can you go forward? And that's what that looks like. So this is the black urine that these patients have when you get excess homogenic acid. And this is due to oxidation of homogenic acid. And you can see that it also binds in tissues, which goes blue, black, green, depending on how much pigment there is. And this is an elbow joint, completely covered with pigment. Okay, can you go forward? And we think this is the sort of biochemical process that leads to it, which is oxidation. But these enzyme systems have never been shown in human. That is a criticism. And again, this is quite old data. Okay, and when we are referring to this in any of the papers we're publishing now, we get real questions. How true is this? And we need to update this, and you can see there, so that's the ochrotic pigment in ligaments. Could you go forward? And you can see when you do it electron microscopy, you can see the pigment. But the interesting thing is, you can see how patchy it is. There's more there, much less there. Okay, and even here, when you look, you can see it seems to attach itself to the periodicity of the collagen. Okay, so we're still trying to understand exactly what's going on, why some tissues are completely clean and others are not. Can you go forward? And this is also seen in macroscopic data, very easy to see. You can see clear areas and you can see black areas. Okay, this is the postmortem I was telling you about, clear areas, black areas. So these are bifurcations. At bifurcation you get more stress, eddies. Okay, same here, aortic bifurcation, so there's more stress. So same with the eye, we think the pull of the muscles, maybe the light damage induced in those areas lying on the side, the pressure from the head, we think with 1 year sometimes is more than the others. So, and you can see even in the aortic root, there's a lot of pigment, high pressure, almost nothing in the pulmonary. So there are a lot of clues here, but I think our unifying mechanism, we think there is damage to tissue, to see if there's anything we can learn in terms of understanding tissue damage in the whole genome sequence that we do. Go forward. Go forward. And of course, that's what it leads to, the effect of the damage. So this is what we see, prostate stones in the majority, about 30%, kidney stones, osteopenia in 60%, fractures, a lot of fractures. Okay, aortic valve stenosis by age 60, you've got it. Ruptures of tendon, ligament, and muscle, large number. In a small group of 70 people, we had about 80 ruptures. Okay, which is just unbelievable. Okay, and 110 joint replacements in 31 people. Okay, that's it's the most extreme phenotype you will see in terms of an OA phenotype. So 10 times as many joint replacements as in standard OA. Okay, can you go forward? So, and there's a lot of variation in the phenotype. Some age is obviously the biggest single influencer of the phenotype, which you will see. I've got a graph there in a minute. And of course, to understand and compare patients, to use this as a tool in clinical trials, we have come up with a way of integrating the morbidity through what is called the AKU Severity Score Index. Okay, that is a way of bringing power to a rare disease, because the NIH clinical trial failed because they carried out the nitisinone intervention in 20 patients, again 20 patients who didn't receive the drug, and of course they were just looking for change in lateral rotation of the hip to decide whether the trial was success after 3 years of nitisinone. Because we realized that wasn't going to work, because think about a cholesterol trial, 20,000 patients to show a difference in heart attacks, 200 heart attacks on one limb and 160 or 150 in the other limb. That's the kind of power you're looking for in terms of numbers. We're never going to have that in AKU. So the way around that is to have a composite score coming together, weighted, so that you can still get good quality information about interventions. This can also be used, after adjusting for age, to compare genes and severity. Okay, it could also in theory be a prediction tool. Okay, so there's very little evidence base for any of the diet or activity in terms of how it influences the phenotype. So there's a 60-year-old with 10 joint replacements, and another 72-year-old, both men, no joint replacement. Okay, there's one patient who had 14 fractures, and there are others who have none. So there's a wide variation in phenotype, and family siblings will have tendon rupture, there are others who don't. Some people have lots of stones, others don't. So we still, are there things we should be looking for that is going to throw up as a marker to say why these guys are different? Is there something else other than HGA that is actually the reason for it? So go forward. And this is the kind of way we score, and you can see we have photographs of the eye and ear in everybody. Okay, digital photographs, and we do audiometry. We obviously have history. We have ultrasound. We have echocardiogram. We have CT bone densitometry. We have PET-CT. We have MRI scans. We have X-rays. We have done everything here. These are the most thoroughly phenotyped patients ever, and we give points and quantify the disease. And you can see how age plays a part. It doesn't matter what feature you look. This is eye pigment scores over time. This is ear pigment scores over time. This is joint scores on isotope scan. And this is the number of joint replacements. And this is all included. Everything shows the same feature, that there's a delay. So meaning that age is the most important influencer, and that there's a steady progression after that. And that again sort of summarizes what I've been saying. Same age, you can see the phenotype difference. The last bit really, I'm nearly finishing now, is about therapy. You know, we are in the era of personalized medicine and precision medicine. So is there anything that whole genome sequencing can tell us in terms of using that in AKU? Of course, this is the treatment for AKU is nitisinone. As I said, AKU is when there's this enzyme which is missing, and of course what nitisinone is doing is inhibiting the enzyme proximal to it, and that means you don't make HGA again, but of course you're already seeing what happens now. You're going to have a lot of tyrosine. Okay, so you now get tyrosinemia. Okay, it's called tyrosinemia type 3. So you have induced tyrosinemia, and of course in the eye the concentration of tyrosine is much higher to provide the melanin that you need for the eye to make sure your eyes work well. And of course it leads to precipitation of tyrosine in the eye in some people, causing problems. Can you just go forward again? And what happens then is you can see the eye is swollen, it is red. Okay, so and that's because of needle-shaped crystals developing in the eye through the slit lamp examination. Okay, can you go forward again? It's not so much a worry when they have symptoms, because we can pick them up, they can tell us, but most of we're seeing more than half are silent. And of course if you don't pick them up and they're out there with this lesion, they could go blind, and of course we don't want them to go blind. So again, we're thinking, are there any ocular genes that might show up when we do whole genome sequence, to why there's only a proportion there which get this, not everybody else. So it might maybe show something else about it. Can you go forward? And of course one of the things about rare diseases is where you get new breakthroughs, things you didn't expect. Serendipity is a wonderful thing, and of course I think one of the things we have already learned quite a lot. This is our group, so this is fame at last. And because we found what's called HDMPs, which is throwing a light on OA as a mechanism for pain in patients with OA. Who knows, we may learn something about osteoarthritis as well when we do it. Okay, so in terms of still about the funding, and the funding, as I said, the NHS England won't fund genetics directly. and in fact also were disappointed at the 100,000 genome project, because I was leading that in Liverpool, and they wouldn't do whole genome sequencing in our AKU patients because we already knew the genetic defect. Okay, which is a bit disappointing. Luckily for us, the European Commission funding is research funding, and we're using that to try and do a whole genome sequencing on these 225 samples. We're slightly worried that this is not a sufficiently large number, but I still think we should have a go. And if there's anything else we should be doing, please tell us, and we would consider. As I said, I'm not a geneticist, but I think this is a great opportunity for AKU to learn something, and if we can find something that benefits other conditions as well and normal people as well, why not? So I'll just stop there.